This video explores the modern fighter jet not simply as a machine, but as a profound paradox, a ghost of metal and fire that is the ultimate expression of both humanity's dream of transcendence and its impulse for destruction. We'll deconstruct this lethal work of art from its predatory airframe woven from mythical materials to the physics-defying technologies that grant it invisibility and the caged star of its engine that gives it life. But to truly understand this creation, how precisely do these core elements of structure, technology, fuel, and materials combine to forge the most sophisticated and terrifyingly beautiful object of our time?
When you stand on the tarmac, with that heat shimmering up from the concrete, and you look at a modern fighter jet, it really makes you wonder, doesn't it? What exactly is this thing? Is it just metal and wires and fuel? Or is it something more? Maybe like a vessel for an idea, or even a kind of physical prayer. It feels like more than just clever engineering. It feels like a testament to human will, maybe. An argument made of titanium and carbon fiber, sort of whispered to these twin gods of, well, transcendence and annihilation.
That's a powerful way to put it.
Yeah.
It really is the ultimate paradox of our time, isn't it? This thing of exquisite, almost terrifying beauty. But like you said, a cathedral built for a terrible faith.
Yeah, exactly. It embodies that ancient dream of flight, the Icarus thing, wanting to break free. But it also taps into something much older, that impulse to dominate.
Absolutely. So understanding this machine, it isn't just about aerodynamics or metallurgy, is it?
No, not at all. It feels more like an act of archaeology, but on the human soul. Using this jet as a mirror, maybe, to uncover the fault lines in our own nature.
Fault lines within ourselves even?
Okay, so let's really unpack this. Our mission today is a proper deep dive. We're going to explore the anatomy of a modern fighter jet piece by piece. We want to get beyond just the shape you see and really dissect the engineering marvel, sure, but also the deeper philosophical questions sort of embedded in its structure, its function. We'll look at everything from its predatory skeleton, you could call it, right through to its synthetic mind, and how each part reflects human ambition or ingenuity, and sometimes, our deepest contradictions.
And we're drawing heavily on some fascinating source material for this journey, Forging a Ghost, the anatomy of a fighter jet. It's our guide through this complex landscape. And what's truly fascinating here, I think, is that this isn't just about the engineering, the nuts and bolts. It's about getting a handle on the deeper implications of technology itself, especially technology like this that really pushes the boundaries of what we even think is possible. And we promise we're going to try and simplify these really complex ideas, make the intricate details of how a fighter jet is designed, how it operates, make it incredibly easy to grasp. We want to reveal how it challenges our ideas about power, about invisibility, and maybe even what it means to be human now in this age of really advanced machines.
So the goal is to give you those aha moments, about this machine that we see images of all the time, but maybe rarely understand in its full depth, its full context.
Exactly, taking you from seeing it to really understanding it.
Okay, let's dive in. Part 1, the skeleton of a predator, form and function. Let's start with the very foundation, the skeleton, or maybe more accurately, its airframe. When you first see one up close, at rest, there's a weird stillness, isn't there?
An alien stillness, yeah. It just sits there on the tarmac like this creature, totally out of its natural element. Silent, almost. Menacing, even when it's cold and quiet.
But its lines, every curve, every edge, they aren't just designed to look cool. They're not some designer's whim.
No, absolutely not. They are the result of brutal, unforgiving calculus. Physics dictates the shape.
Every subtle blend, like where the wing meets the fuselage. It's like a whispered word in this long, violent conversation the jet is having with the air, sculpted purely by the demands of physics, especially at high speed.
And it's so important to contrast this with, say, a commercial airliner. An airliner's shape, it's all gentle curves, a blunt nose. It's designed to kind of placate the atmosphere.
Politely request passage,
Exactly. Its whole form is optimized for smooth, efficient flight, carrying hundreds of people safely, comfortably over huge distances. That's its job.
But a fighter jet, its shape is designed to conquer the atmosphere, to rip through it with the absolute minimum drag and maximum authority.
Its purpose isn't gentle passage at all. It's aggressive assertion. It's this constant battle against the air it flies through.
And you see that philosophy everywhere. Look at the leading edges of the wings. They're honed, almost knife sharp.
Yeah, honed to a fineness that looks like it could literally slice the wind itself. They're not rounded or blunt like in airliners. They're precise, sharp, almost blade-like.
And that's crucial for cutting through the air cleanly, right? Minimal resistance, maximum efficiency, especially when you're talking supersonic speeds.
Absolutely critical.
Yeah.
And then think about the tail fins. You often see them canted at these strange, unsettling angles. Sometimes even swept forward slightly on designs like the Su-47, though that's rare.
They don't look like a normal plane's tail.
Not at all. These aren't just for basic steering like a bird's tail feathers helping it balance. In a modern fighter, these fins, the vertical stabilizers, the horizontal ones, sometimes they're combined into ailerons on delta wings. They're essentially rudders for what you can only describe as a ballet of impossible violence.
Wow, a ballet of violence.
They allow the machine to pivot on an axis of pure aggression. They enable these extreme high-G maneuvers that would literally tear a lesser aircraft apart.
You mean like pulling 9Gs, turning incredibly tightly?
Exactly. Think of an F-22 or an F-35, those sharply angled twin tails. That geometry is crucial. It helps control the airflow at supersonic speeds, provides stability when the aircraft is pulling really high angles of attack flying nose up relative to the airflow.
And this whole design philosophy, this architecture of a predator, as you called it, it's evolved over time, hasn't it?
Oh, absolutely. Refined over a century of aerial warfare. Each new design learns from and critically counters its predecessors. It's a fascinating lineage.
So you can see influences from older planes.
Definitely. When you look at a modern fighter, you can almost sense the ghost of the P-51 Mustang and its relentless pursuit of speed and performance. Maybe the echo of the MiG-15, its raw agility. The phantom limb of the F-4 Phantom and its brute power and multi-role capability.
It's like they're all related.
They are. Each generation is a direct response to the last. It's like this closed, circular ecosystem up there in the sky where each new apex predator emerges specifically designed to hunt its own kind, always pushing the boundaries of what's possible in air combat.
And it's not just the shape, is it? It's what that shape is made of. The materials are just as critical as the form itself.
Absolutely fundamental. For decades, aluminum was king. It was the light, loyal servant of aviation.
Right. Things like Duralumin back in the day.
Exactly. Those alloys revolutionized aircraft construction early on, made planes lighter, faster, stronger. It was indispensable for generations, from biplanes right up to sleek jet airliners.
But it had its limits.
It did. As speeds kept climbing, especially into the supersonic realm, and as maneuverability demanded pulling higher and higher G-forces, aluminum started to, well, fail.
How so?
It would warp under the intense heat generated by air friction at Mach 2 or 3. It would fatigue, develop micro cracks from being constantly stressed in high G turns. Eventually, it would just surrender to the immense demands.
So it couldn't keep up with the performance requirements.
Precisely. It couldn't handle the combination of extreme speed, agility, and the heat loads involved.
So engineers needed something tougher.
Yeah. They turned to something quite different. A metal that almost sounds like something from mythology. Titanium.
Named after the Titans, right?
Exactly, which perfectly captures its essence, I think. Titanium seems to possess this kind of primordial defiance in its very structure.
What makes it so special?
Well, first, it's incredibly strong. As strong as some types of steel, actually. But, and this is crucial for aircraft, it's nearly half the weight.
Ah, the strength-to-weight ratio. Always key in aerospace.
Always. And what's more, it treats extreme heat with what you could only call aristocratic disdain.
It just shrugs it off.
Pretty much. It maintains its structural integrity, resists that slow deformation under stress at high temperatures, even when things get incredibly hot.
Like from air friction or near the engines.
Exactly. Friction at Mach 3 generates enormous heat on the skin. Engine exhausts are obviously incredibly hot. Missile launches create intense thermal shock. Titanium handles it. That's why you find it in critical, high-load, high-heat areas.
Like engine components, firewalls between the engine and fuselage. Key structural spars in the wings near the engine.
Precisely those spots, but working with it. That's another story. It's notoriously difficult to machine, to weld.
So making parts from it is hard.
Very. To forge a complex part like a main wing spar box or a landing gear beam from titanium, it's not just manufacturing. It feels more like modern alchemy. You're wrestling this divinely stubborn material into a precise shape that has to serve a human purpose and withstand insane conditions.
But even titanium has its limits, right? Especially when you start thinking about, well, invisibility, stealth.
Exactly. The newest generations of these aerial ghosts, these specters, They're not primarily forged from metal anymore. They are quite literally woven.
Woven? What do you mean?
They're made from advanced composite materials, mostly layers upon layers of carbon fiber.
Carbon fiber, like in high-end sports cars or racing bikes?
Sort of, but taken to an entirely different level. Imagine threads, each one finer than a human hair, woven into a fabric. Then that fabric is impregnated with a special polymer resin.
Okay.
Then you stack layers of this resin-impregnated fabric in specific orientations in a mold. And finally, you bake the whole thing into existence under immense pressure and heat inside a giant oven called an autoclave.
So it's like baking a cake, but the cake is a wing?
Huh. A very, very strong, very light, very expensive cake, yes. It's almost like using a loom, but instead of weaving cloth, you're weaving this substance that's stronger and lighter than pretty much any metal we use in aircraft. And crucially, it has properties that help make the aircraft stealthy.
How does it behave differently from metal?
Well, it's not like the solid, predictable honesty of steel or aluminum. Composites offer what you might call a black matte deception. A wing made of carbon fiber is solid, yes, but it behaves more like a bundle of discrete strengths.
What does that mean, discrete strengths?
Engineers can strategically layer these carbon fiber fabrics at different angles, say 0 degrees, plus 45, minus 45, 90 degrees. Each orientation is strong against a specific type of stress, like tension, compression, or shear.
So you tailor the strength exactly where it's needed.
Precisely. You align the fibers to counter the specific forces that part will experience in flight. This anisotropic property, where the strength varies with direction, is what gives composites their incredible strength-to-weight ratio. Metals are isotropic, they're generally the same strength in all directions. Composites let you be much smarter, much more efficient.
It's in the result.
The entire machine becomes more of a unified whole, not just a collection of metal parts bolted and riveted together, but closer to a single, continuous expression of purpose. Optimized for performance, reduced weight, and crucially, a minimal radar signature.
So this shift in materials, it's more than just technology.
Oh, much more. It's a profound philosophical shift, really. We've moved from sculpting a beast out of the Earth's heaviest, strongest elements like titanium to literally weaving one from these threads of pure potential, these carbon fibers.
Weaving a ghost.
Exactly. It creates a strength that is both immense and, in a way, eerily hollow. It's the perfect material for forging a ghost. Something of profound substance that, from certain perspectives, especially a radar's perspective, seems to be made of almost nothing at all.
The key insight being that we're not just building with materials anymore, we're designing the material itself for the job.
That's the leap, intelligently designing the material's properties to meet these unprecedented demands of performance and invisibility.
Okay, that leads us perfectly into part 2, the skin of invisibility, the art of disappearance. So if the airframe is the skeleton, then its skin is. Well, it feels like its defining feature is its profound lack of soul, maybe. Its main job is not to be seen.
That's a great way to put it. It's designed purely to disappear. And this is the realm of stealth technology, which honestly often feels less like hard science and more like some kind of technological magic.
It's so counterintuitive, isn't it? We expect to see big, fast things moving through the sky. These machines mess with that basic expectation.
They absolutely do. And the common story, the simple version we tell ourselves, is that stealth makes an aircraft invisible to radar. Poof, gone.
But it's not that simple.
Not even close.
Yeah.
The truth is far stranger and maybe more unsettling. You can't make an aircraft truly physically invisible. The laws of physics just aren't that cooperative, unfortunately.
So what does stealth do?
Instead of making it invisible, it aims to make the aircraft effectively silent in the specific language that its enemies speak. And that primary language is radar.
Okay, silent in the language of radar. How?
Well, first you have to understand radar itself. Think of it like a conversation maybe, or like sonar, but with radio waves. A radar system sends out a shout, a pulse of high-frequency electromagnetic energy.
Right.
And then it carefully listens for the echo, the signal that bounces off any objects in the path of that shout.
So a normal plane, like an airliner or an older fighter.
A conventional aircraft, yeah, with its rounded fuselage, its vertical tail fins, all those right angles where wings meet body, where weapons pylons hang. It's a loud, boisterous participant in this radar conversation.
It shouts back, clearly.
It screams back, "I am here, definitely here." Its shape acts like a pretty good reflector, sending a strong, clear, unmistakable signal right back to the radar receiver. Makes it relatively easy to detect, track, and target.
Okay, so how does a stealth aircraft avoid that? How does it become a master of obfuscation, as the source calls it?
Well, the first trick is geometry. Its skin isn't smooth and curved in the ways we think of as aerodynamic traditionally. Instead, it's often a mosaic of flat planes and sharp angles, a faceted sculpture.
Like the F-117 Nighthawk, the original stealth fighter, all those flat panels.
Exactly like the F-117. Although modern designs like the F-22 and F-35 are much more sophisticated, blending those stealthy shapes with better aerodynamic performance. But the principle is the same. And interestingly, this whole philosophy came partly from work by a Soviet physicist, Pyotr Ufantsev, back in the 60s.
Really? A Soviet physicist helped develop American stealth?
Inadvertently, yes. His obscure paper detailed how to mathematically calculate radar reflection from simple 2D and 3D shapes. Lockheed engineers realized his formulas could be used in reverse to design shapes that would reflect radar waves away from the source.
So the angles don't absorb the radar, they deflect it?
Primarily, yes. They act like a badly angled mirror. Instead of reflecting the radar shout back towards the listener, the radar receiver, these precisely calculated facets scatter the energy away in thousands of other directions.
Like shattering a mirror, sending light everywhere except back at you.
That's a perfect analogy. The angles are meticulously designed so that the bulk of the radar energy bounces off in specific controlled directions, mostly away from the radar that sent it.
So what does the radar hear?
When the enemy radar shouts, the ghost whispers back. Maybe a nonsensical, fragmented reply, or ideally, almost no reply at all. On the radar screen, it doesn't show up as a solid, consistent track. It might appear as just a fleeting anomaly, a bit of random digital noise, maybe something the size of a bird, a blip that doesn't behave like a threatening aircraft.
And by the time they figure out what it might be...
If they ever do, the ghost is already gone, or it's already completed its mission. That critical delay, denying the enemy those precious seconds to react, to target, to engage. That's a huge part of what stealth provides.
Okay, that geometric shaping is incredible, but you mentioned there's more to it, another layer.
Yes, the geometric shaping is step one. Step two involves the skin itself being coated in or even made with special radar absorbent material, RAM.
RAM, and this isn't just paint.
Oh no, definitely not just paint. It's often described as a top-secret cocktail. It contains things like microscopic ferrite particles, tiny iron-based magnetic spheres suspended in special polymer matrices, sometimes carbon-based materials too. It's often applied in carefully calibrated layers. This stuff is a shroud.
A shroud. And its job is different from the shaping.
Completely different, but complementary. While the shape deflects radar waves, the RAM is designed to actually absorb their energy.
Absorb it? How?
When radar waves, those electromagnetic waves, do manage to strike the RAM coating directly, instead of bouncing off, their energy gets converted. The material essentially turns that radio wave energy into a tiny, almost imperceptible amount of heat.
So it just smothers the signal.
Effectively, yes. Different types of RAM are optimized for different radar frequency bands. Some use dielectric properties, others use magnetic loss properties to convert and dissipate that incoming radar energy.
So you get a double whammy.
Exactly. The ghost shape deflects the shout away, and whatever energy does hit it gets devoured by the RAM coating. It's this combination, the shaping and the absorption, that massively reduces the aircraft's overall radar cross-section. It's RCS.
RCS being how big it looks on radar.
Precisely. A conventional fighter might have an RCS the size of a large truck. A stealth fighter aims for an RCS maybe the size of a golf ball or even a marble from certain angles. That makes it incredibly difficult to detect, extremely hard to track consistently, and almost impossible to get a missile lock on with traditional radar guidance.
You called this a violation of the natural order earlier. What did you mean?
Well, think about it. As humans, our entire experience is based on the expectation that we can perceive what is physically present. We see things, we hear things. This machine, through incredibly clever engineering and material science, fundamentally exploits that expectation.
It breaks the rules of perception.
It creates this localized pocket of effective non-existence, at least in the radar spectrum, an area where the normal rules are suspended by technological decree. It's about dominating the information space, controlling what the adversary can and cannot know, forcing them into uncertainty.
It's not just a technological edge then, it's psychological warfare too.
Profoundly psychological, yes.
And that leads back to that deeper question. What does it mean for a nation, for us as a species, to strive not just for strength, but for this kind of perceptual dominance?
It's a heavy question. It's not just wanting the biggest stick anymore. It's wanting the stick that cannot be seen.
The desire to see without being seen, to act without being witnessed, to deliver a consequence without an observable cause.
It's the posture of a god, isn't it? Or perhaps, as the source suggests, a demon. What does it say about us that we dedicate such immense ingenuity and resources to perfecting this art of disappearance?
It's unsettling. And you mentioned the ground crews, the people who maintain these planes.
Yes. It's fascinating. They talk about the skin, the RAM coatings, with this incredible reverence, almost like it's a sacred trust.
Why? Because it's so sensitive.
Extremely. They have to meticulously patch any damage, cure the materials correctly, protect it constantly from weather, even from casual bumps and scrapes. They often work in specialized, climate-controlled hangars using highly specific techniques.
Because any little flaw can compromise the stealth.
Exactly. A tiny scratch, a poorly sealed panel, even certain types of dirt or residue can potentially increase the RCS, turning that whisper back into something closer to a shout. So these technicians become like tenders of a sacred relic.
Polishing the surface of a void.
That's a beautiful way to put it. Meticulously maintaining an absence, preserving that fragile cloak that allows this machine and its pilot to move through the world for a time as an unseen force. It's a remarkable, demanding responsibility.
Wow. Okay, let's move from the skin inwards to the heart. Part 3. The heart of a captured star, the jet engine. So we've got the predatory skeleton, the invisible skin. Now deep inside that woven, unseen shell lies the true heart. And the heart of a fighter jet, it's not like our hearts, is it? It's not quiet, rhythmic life.
No, not at all. It is a furnace. The modern jet turbine engine.
Yeah.
It's less an engine in the way we think of a car engine and more a controlled continuous explosion.
A self-contained hurricane of fire.
That's a great description. It's an incredible feat of engineering that generates unbelievable power by harnessing the raw energy of combustion and gas expansion.
Okay, walk us through it. You said earlier, follow a molecule of air. Where does it start?
Right. Here's where it gets really interesting. First, that air molecule is violently sucked into the massive intake at the front of the engine, often at nearly the speed of sound itself. These intakes are huge maws designed to swallow colossal amounts of air. From there, it rushes into the compressor section. This isn't just one big fan. It's a series of multiple spinning discs called stages, each lined with thousands of incredibly precise airfoil-shaped blades.
Like lots of fans stacked together.
Exactly. And each stage compresses the air a little bit more, forcing it into an ever smaller volume. As this happens, the pressure skyrockets and the temperature climbs dramatically.
How hot and how much pressure?
We're talking hundreds of degrees Celsius, and pressures maybe 30, 40, even 50 times higher than the atmospheric pressure outside. That air, which started as just, well, air, is now this incredibly dense, superheated fluid, primed for combustion.
Okay, primed and ready. What's next?
Next, it enters the combustion chamber, or the combustor. Here, this highly compressed, super hot air is mixed with a fine mist of jet fuel, sprayed in through sophisticated fuel nozzles.
And this fuel isn't like gasoline.
No, it's a highly refined type of kerosene, usually designated JP8 for military use, or Jet A1 for commercial, though they're similar. It's engineered for high energy density, clean burning, and stability under extreme conditions. It's less a liquid fuel, more like liquid energy waiting to be unleashed.
So hot compressed air meets fuel mist, then ignition.
Ignition is usually started by an igniter, kind of like a high energy spark plug. But once the fire starts, the process is continuous and self-sustaining as long as air and fuel keep flowing in.
And it's not a gentle burn, I take it.
Instantaneous and total combustion is the goal. It's not a flicker, it's a torrent of flame. A sun in miniature erupts inside that chamber. Temperatures can soar past 1700 degrees Celsius.
That's hotter than the melting point of many metals.
Absolutely. Which is why the combustion chamber, and especially the turbine blades downstream, are made of exotic superalloys and often have incredibly complex internal cooling channels, bleeding cooler air from the compressor over their surfaces just to survive.
Okay, so this massive explosion happens. Where does the energy go?
Those incredibly hot, rapidly expanding gases have only one way to go: out the back. But first, they have to blast their way through another set of complex bladed wheels, the turbine section.
The turbine. What does that do?
The sheer force of these expanding exhaust gases spins the turbine blades at incredible speeds, tens of thousands of revolutions per minute, maybe 20,000, 30,000 RPM or more.
And why is that spinning important?
It's absolutely crucial, because the turbine is collected by a central shaft back to the compressor section at the front. So the energy extracted by the turbine is what drives the compressor, which keeps sucking in and compressing new air.
Creating this self-sustaining cycle.
Exactly. A cycle of self-sustaining controlled violence. Yeah. Intake, compression, combustion, expansion through the turbine, which drives the compression, Round and round it goes.
And the leftover energy, the gas is blasting out the back?
That's the thrust. The sheer reaction force of accelerating that mass of superhot gas out the nozzle at high speed is what propels the aircraft forward with incredible force.
And that sound, that deafening roar.
It's not just machinery noise, is it? It's the sound of the air itself being torn apart, burned, chemically altered, and then reborn as pure raw thrust.
But sometimes that's not enough. There's the afterburner.
The afterburner, or reheat, as it's sometimes called. This truly is, as the source says, an act of spectacular, elegant insanity.
What does it actually do?
Okay, so after the hot gases have passed through the main combustion chamber and spun the turbine, they still contain a lot of unburned oxygen because the initial combustion is kept fuel lean to manage temperatures.
Right.
The afterburner section is essentially a simple pipe behind the turbine. And what it does is spray raw fuel directly into these searing hot exhaust gases.
More fuel into the exhaust.
Exactly. Because there's still oxygen and it's incredibly hot, this extra fuel ignites instantly in a secondary, much less controlled, colossal explosion.
And that's the flame you see shooting out the back.
That's the huge plume of blue and orange flame you see, sometimes stretching many meters behind the aircraft. It's a visible spear of incandescent power.
And the effect on thrust.
It can dramatically increase the engine's thrust, sometimes by 50%, sometimes nearly doubling it, depending on the engine design and conditions.
Wow. So when would a pilot use that?
For moments of extreme need, rapid takeoffs, especially from short fields or aircraft carriers. Breaking the sound barrier going supersonic often requires afterburner. High-G combat maneuvering, escaping a threat quickly, or performing rapid climbs, like going vertical, almost as if gravity is just a suggestion.
But there's a downside.
Oh yeah, it's brutally inefficient. It guzzles fuel at a terrifying rate. Using afterburner can empty an aircraft's fuel tanks in a matter of minutes, compared to hours in normal cruise.
So it's only for short bursts?
Absolutely. A few critical moments when survival or mission success demands that absolute maximum surge of power. It really is the machine's primal scream. A raw, unrestrained outpouring of pure, destructive energy.
And the fuel itself, you called it the blood of the ghost earlier.
Metaphorically, yes. That JP8, that highly refined kerosene, it's the life force that enables all this fire and fury.
And thinking about where it comes from.
It's quite profound, isn't it? It's the distilled essence of ancient sunlight. The compressed, transformed remains of prehistoric forests, algae, plankton, life that lived millions of years ago, pumped up from deep within the earth, refined into this incredibly energy-dense substance.
So every flight is burning ancient history.
Literally. Every single sortie, every training mission burns through thousands of pounds, thousands of gallons of this stuff. An F-16 might burn, 8,000 pounds an hour in normal flight? Much more in afterburner?
So the ghost is sustained by a diet of deep time.
Consuming millions of years of stored solar energy, millions of years of life, in just a few hours of flight. It's a strange, almost dark poetry to it.
His paradox, the most advanced creation of our age.
Powered by the most ancient of energy sources, flying into the future literally on the ashes of the distant past.
It's Icarus again, but different.
Yeah. This time, he hasn't flown too close to the sun. He's figured out how to rip a piece of the sun out, cage it inside a heart of titanium and superalloys, and use it to soar higher and faster than anyone ever dreamed.
The InSight, being our most cutting-edge tech, is still fundamentally tied to Earth's deep geological history.
Absolutely. We're burning the past to fuel the future.
Okay. Skeleton, skin, heart. What about the mind? Part 4. The nervous system of a demigod. The pilot machine fusion. So this incredible machine, predator skeleton, invisible skin, fiery heart. But as you said, it has no mind of its own.
None at all. The intelligence, the will, the decision-making that resides entirely within the cockpit.
Which is usually a pretty cramped space, right?
Surprisingly so. Often barely bigger than a small closet, filled with the green or amber glow of multiple screens, the quiet hum of computers and cooling fans, and an array of buttons, switches, and controls designed for ultimate precision under pressure.
And it's here that the line between human and machine gets really blurry.
It dissolves. This is the nexus. The place where the pilot doesn't just operate the machine, they merge with it, becoming an extension of its senses and capabilities.
Now, the old image, the pilot gripping a joystick, physically connected by cables and pulleys to the wings and tail, that's mostly gone in advanced fighters, right?
That's largely romantic fiction now, yeah. At least for primary flight controls in aircraft like the F-16, F-22, F-35, Eurofighter, Rafale.
So how does it work? What's fly-by-wire?
Okay, so when the pilot moves the control stick or pushes the rudder pedals, they're not directly moving control surfaces anymore. Those inputs are converted into electronic signals. They're essentially a request sent to a suite of powerful onboard flight control computers.
A request? Like, I'd like to turn left now, please.
Basically, yes. My intent is to roll left at this rate. The computer then takes that request, but it also looks at literally thousands of other data points every second.
What kind of data?
Airspeed, altitude, angle of attack, how the wing is meeting the airflow, G-force being pulled, the aircraft's current roll, pitch, and yaw rates, wing loading, fuel weight and balance, engine thrust setting, even things like whether the landing gear or flaps are down.
Okay, a ton of information.
An avalanche of data. And the computer uses all of this to translate the pilot's simple intent turn left into a series of incredibly minute, precise, and often coordinated adjustments to multiple control surfaces simultaneously. Ailerons, elevators, rudders, maybe even leading-edge flaps.
All orchestrated by the computer to achieve the pilot's goal.
Exactly. To achieve the desired maneuver efficiently and safely, while keeping the aircraft stable and preventing it from departing controlled flight.
And the computer can do this faster than a human.
Far, far faster and more accurately than any human nervous system could manage directly. It's constantly making tiny micro adjustments to keep the plane flying smoothly, even in turbulence or during aggressive maneuvers.
And it provides protection.
Absolutely. A key feature is flight envelope protection. The computers know the aircraft's limits, maximum G-load, maximum angle of attack before stalling, structural limits. They simply will not allow the pilot to command a maneuver that exceeds those limits.
So the pilot can't accidentally rip the wings off or put the plane into an unrecoverable spin.
Generally, no. The system prevents it. Which means the pilot doesn't have to constantly worry about the mechanics of flying the plane right at the edge.
So their role changes.
Fundamentally, the pilot isn't a driver anymore, directly wrestling with physics through cables. They're more like a high-level systems manager, a conductor leading an orchestra of automated systems. Or, as the source puts it, they become the ghost in the machine, guiding its immense power rather than directly wielding it.
And this frees them up mentally.
Hugely. It offloads enormous cognitive burden, allowing the pilot to focus less on flying the plane and more on the tactical situation, finding the enemy, managing threats, employing weapons, communicating. Their brain power goes towards strategy, not just mechanics.
And their perception of the world, that changes too, doesn't it? With things like helmet-mounted displays.
Completely transformed. It's no longer just human eyesight looking out a window. Through their helmet-mounted display, the HMD, the real physical world outside the canopy, gets overlaid with this dynamic stream of digital information.
What kind of information?
Threat warnings, locations of enemy aircraft or missiles, locations of friendly forces, blue force tracking, target data, weapon aiming cues, crucial flight parameters like airspeed, altitude, heading. It's all projected right onto the visor glass, floating in their field of view.
So they don't need to keep looking down at the instrument panel.
Much less so. Key information is fused directly with their vision of the outside world. It creates this augmented reality, tailored specifically for air combat.
And the world itself starts to look different.
It literally becomes a landscape of data. A mountain range isn't just scenery, it's potential terrain masking from enemy radar. A building on the ground isn't just a structure, it's a potential target or landmark, represented by a symbol on their display, maybe with range and targeting information already calculated.
Wow. And this augmented view is fed by the jet's own senses, right? Like its radar.
Absolutely. And modern fighter radar is incredible. We're talking about Active Electronically Scanned Array, or AESA radar.
AESA, how is that different from older radars?
Older radars had a mechanical dish antenna that physically moved back and forth or up and down to scan the sky. AESA radar is totally different. It's a flat, stationary plate made up of hundreds, sometimes thousands, of tiny individual transmit-received modules.
Like tiny little radars all working together.
Exactly. And because there are no moving parts, it can steer its radar beams electronically, almost instantaneously, in any direction. This makes it incredibly agile and allows it to do multiple things at once, what they call multifunctionality.
Like what?
An AESA radar can be scanning the sky for airborne targets, simultaneously creating a high-resolution map of the ground below, tracking moving vehicles, acting as a jammer against enemy radars, and functioning as a high-bandwidth data link to share information with other aircraft or ground stations, all potentially at the same time.
That's incredible versatility.
It really is, and it can track dozens, sometimes hundreds, of targets simultaneously, building this incredibly detailed, almost godlike picture of the entire battle space, extending out for huge distances.
And it's harder for the enemy to detect the ESA radar itself.
Yes, that's another huge advantage. Techniques like low probability of intercept detection, LPI/LPD, allow it to operate much more stealthily than older radars, spreading its energy across frequencies or using very directed beams, making it harder for enemy warning receivers to pick up.
Okay, so the ESA provides this amazing picture, but you mentioned sensor fusion.
Right, the AESA is just one sensor, albeit a primary one. Modern fighters are packed with other sensors too, things like infrared search and track systems, or AEST.
What do they do?
IS systems passively scan for the heat signatures of other aircraft engine exhaust plumes, friction heat on the skin.
Yeah.
Because they're passive, they don't emit any energy, they can detect targets without revealing the fighter's own position, which is great for stealth.
So you have radar, infrared, what else?
Advanced electronic warfare, EW suites, that listen for enemy radar or communication signals, identify them, locate them, and can potentially jam them. There are also secure data links connecting the fighter to a wider network, other fighters, AWCS command and control aircraft, satellites, drones, ground commanders.
So information is coming from everywhere.
Exactly. And sensor fusion is the process where the aircraft's central mission computer takes all this raw data from all these different sensors, its own radar, IRST, EW, plus all the offboard data coming in via data links, and intelligently combines it.
Combines it how?
It correlates the contacts, figures out if the radar blip and the heat signature are the same target, weighs the reliability of different data sources, resolves conflicts, and then synthesizes it all into a single, unified, coherent, and highly accurate picture of reality.
One clear picture for the pilot.
One clear, understandable, actionable picture presented on their cockpit displays and helmet visor, eliminating ambiguity, reducing workload, and dramatically improving situational awareness. It's like giving the pilot a dozen different inhuman senses and then fusing them into one superhuman perception.
And the pilot sits at the center of all this.
Right at the center of this incredibly complex web of perception, this synthetic consciousness, they become the crucial node in this vast network. A human processor, ultimately, tasked with interpreting this fused reality and making the final, often terrible decision.
And does this change the nature of combat itself?
Profoundly. The act of combat becomes increasingly abstracted, almost sanitized from the pilot's perspective. The enemy aircraft isn't another pilot in another machine. It's reduced to a green diamond or a red triangle on a screen, a symbol with data attached.
And firing a weapon.
Releasing a weapon might be just the press of a button on the control stick. The missile flies off, guided by data from the sensors of the network, and the result might just be that symbol disappearing from the screen, or a confirmation message relayed back from another asset miles away. A distant flash, maybe, but often not even that.
So it creates distance.
An experience of both profound power, the ability to see and strike from incredible distances, often without being seen, and paradoxically, profound detachment. And this, I think, circles back to one of the most critical questions the source raises. Has this incredible fusion of human and machine truly created a superior warrior? Or has it perhaps created something potentially more dangerous?
More dangerous how?
A being who can wield apocalyptic levels of power, launch weapons that can devastate targets miles away, but without feeling the immediate visceral weight of that act.
The emotional distance that technology can create.
Exactly. While technology undeniably amplifies our physical and perceptual capabilities, does it also risk creating this profound moral and emotional distance? Does it blur the lines of responsibility, mask the true human cost of conflict?
The pilot looks through the machine's eyes, thinks with the machine's brain.
And in doing so, perhaps risks losing, or at least suppressing, a part of what makes them human. The visceral reality of combat gets replaced by data points, abstract symbols, tactical problems to be solved. And that distance, it's something we really need to grapple with. It's deeply disquieting.
Okay, let's bring this deep dive toward its conclusion, the outro. So when the mission's over, the engines finally fall silent, that immense heat bleeds away from the skin, the Ghost rests.
It becomes an object again. Metal, composites, wires, sitting inert on the ramp, its incredible power coiled back up inside it, like a sleeping serpent.
But hopefully for us, something has changed in our understanding. This journey through its anatomy, its predatory bones, its invisible skin, its captured star heart, and its synthetic mind. It hasn't necessarily led us to simple answers, has it?
No, if anything, it's led us to a deeper, maybe more profound mystery. A mystery about the technology, yes, but ultimately a mystery about ourselves.
So what does it all mean for us?
Well, fundamentally, we built this thing. We dreamed it into being. It stands as this undeniable testament to our highest intelligence, our most disciplined engineering, our most creative problem-solving impulses.
It shows what we're capable of, mastering the physical world, pushing boundaries.
Enabling feats that were pure science fiction just generations ago. It's an incredible symbol of human capability.
And yet,
It is designed, engineered, optimized for the sole, terrifying purpose of undoing creation, of destruction.
it's a monument to our own internal contradiction.
Perfectly put. The Promethean fire of human genius used to light the fuse of our own potential destruction.
Stand before one, maybe, in the gathering dusk. The ground crew moving around it, those tenders of the void, in their practiced, almost reverent silence. It seems like it's waiting.
It feels like an answer, doesn't it? An answer to that millennia-old question, what is the ultimate expression of human will and power?
But as you stare into that dark, reflective canopy, maybe where the pilot's eyes would be, you realize it's also asking us a question.
It is. It asks us, now that you've built me, now that you possess this capability to move like a phantom and strike like lightning, what will you do with it?
Now that you have forged this ghost to command the sky, can you control the other ghosts? The ones you've maybe unleashed within yourselves?
That impulse for dominance, the detachment from consequence, that hunger for unseen, unaccountable power.
It feels like a doorway has been opened.
And we're standing right on the threshold, mesmerized maybe by the terrible beauty of what we've created, feeling the silent thrum of its potential power.
And we don't really know if it's a doorway to heaven or to the abyss.
We only know that we are the ones who built it, and we cannot turn back.
If you enjoy this video, please like, share, subscribe and hit the bell to the later update from my channel. Thank you for watching till the end and see you in the next video.